solving trig equations, you want to remember that these are different than verifying trig identities. Trig identities are true for all values in the domain, and you have to make the replacements and simplify a side down until it transitions into the other side. When solving trig equations, you actually are back to thinking about the algebraic methods you use to solve an equation, as well as sometimes needing to use some trig identity replacements to be able to transition it into a form that you're able to use the algebraic methods in order to solve it. Now, another thing you want to consider is that you need to leave your answers in the form that they've requested. So when it gives you the directions for a question, or when you're doing an application where in real life you know what type of setting it needs to be in, you always want to be mindful that you answer your angles to the trig equations in the span and in the form that it's requesting. So when here it says that x is from 0 to just up to but not including 2 pi, I know that I'm supposed to give my answers in radians, and I know I'm supposed to just do the positive angles with that first rotation around. So let's look at some examples. The first one is the square root of 3 sine x is equal to negative cosine x. Well, this one's a little problematic because it doesn't have the same trig function in it. It is acting on the same angle, so it's not like a double angle or a half angle identity that I can go into. So when I'm looking at that, at first I want to get at least a 0 on one side, so I'll add the cosine x to both sides. And then I want to recall that I have an identity that lets me transition the sum or difference of a sine function and a cosine function when they're adding or acting on the same angle back into an amplitude change and phase shift of a sine function. So just kind of recalling that off to the side, if I have a sine x plus b cosine x, I can write that as k times the sine of x plus alpha, where k is the square root of a squared plus b squared, and alpha is the angle such that the sine of alpha is the coefficient in front of the cosine over that k, so b over k, and the cosine of alpha also has to be the coefficient in front of the sine over k, so my a over k. Looking at this then, I have a is the square root of 3, and b is the coefficient in front of cosine, and since there's not one showing, b is equal to 1. So now running that through this formula, if I have k is the square root of a squared plus b squared, k is going to be the square root of 3 squared plus 1 squared. Well, the square root of 3 squared is 3, and 1 squared is 1, so 3 plus 1 is a 4 under the square root, and the square root of 4 is 2. Then I have that the alpha that we're looking for to transition it to this, I need to set it up that the sine of that alpha is 1 over 2, or 1/2, and the cosine of that angle alpha is the square root of 3 over that k, so square root of 3 over 2. So the angle that has a sine ratio of 1/2 and a cosine ratio of the square root of 3 over 2, so think backwards on your unit circle, the angle that has a cosine ratio of the positive of the square root of 3 over 2 and a sine ratio of positive 1/2 is a quadrant 1 angle, and it's actually pi over 6. So this equation right here transitions into k2 times the sine of x plus pi over 6. And that's equal to 0. So now I was able to put it compactly as a sine function of an angle. Now we're going to divide both sides by 2. I get the sine of x plus pi over 6 is equal to 0. And then we did divide both sides by 2, but 0 divided by 2 is still 0. Now, think of this is the angle that we're going to set equal to the angles that make this true. So the sine of the angle comes out 0. Well, where is sine 0? Sine is 0 at 0 and at pi. So I have x plus pi over 6 is equal to 0. X plus pi over 6 is equal to pi. And sine is 0 also at 2 pi. Now I know if this were just an x, I wouldn't set it equal to 2 pi because that would be out of our range. But I know that I'm going to have to subtract a pi over 6 from both sides to find my x. And in this first one, I'm going to get a negative pi over 6 that I can't report because I can only report the angles from 0 to 2 pi. So I needed to keep going one more time to x plus pi over 6. Sine is 0 also at 2 pi. So subtracting pi over 6 from both sides, I get x equals negative pi over 6, but that's not a reporting value because my angles have to be between 0 and 2 pi. Subtract pi over 6 from both sides in the next one. Pi, subtract a pi over 6. Well, pi is 6 pi over 6. Subtract 1 pi over 6 gives me 5 pi over 6. And then take 2 pi and subtract a pi over 6. Well, 2 pi is 12 pi over 6 minus 1 pi over 6 would be 11 pi over 6. So those are the values of x that will make this original equation true that also are within the span of angles that they've asked me to report it in. Okay, let's go to part B. Part B is tangent squared x is equal to tangent x. Well, let's think back to the algebra on this. Remember, tangent squared x is tangent x quantity squared. And that would give me a tangent x that's squared and a tangent x is to the first power on the other side. Algebraically, think that would be like a squared is equal to a. Now with this, we can't divide both sides by a because a might be 0 sometimes. I can't divide both sides of this by tangent x because tangent x could be 0 sometimes and you can't divide by 0. What you need to do is subtract that term over and then factor, and then we would set each factor equal to 0 and solve. But I'm going to stop at the algebraic part right here because I'm really interested in doing this pattern of thought on the trig equation. So we're going to subtract the tan x from both sides. So I'll have tangent squared x minus tangent x is equal to 0. We're going to factor out the tangent x. Then we're going to set each factor equal to 0, so either tangent x equals 0 or tangent x is equal to 1. And then we're going to give all the angles in the span from 0 up and 2 but not including 2 pi that this would be true for. Okay, so for what angles in the span from 0 up 2 but not including 2 pi do you get a tangent ratio of 0? Well, it happens at 0. Because it happens every time that the sine is 0 but the cosine isn't, because tangent of x is sine x over cosine x. So that would be at 0. That would be at pi. And while it's true that it also would be at 2 pi, I'm not going to write it down because there's not an or equal to there. Now, when is the tangent of x positive 1? Well, the tangent of x is positive 1 at those angles x that are the pi over 4s. And it's at the one where you would have the x and y coordinates both having the same sign, because then positive divided by positive is positive and negative divided by negative is positive. So tangent of x will be 1 at pi over 4, the first quadrant over 4 angle. And then also in the third quadrant. And the pi over 4 reference angle would take me down into third quadrant where I would have pi plus a pi over 4, so that would be at 5 pi over 4. So those are our values of x for that. Okay, and then part C, and I've kind of crouched that in. So I'm going to take a moment to erase is cosine 2x is equal to 2 cosine x minus 1. Now here, when I look at it, I can't straight away go into an algebra thought process because I don't have the trig function acting on the same angle. I have cosine of 2x, and then over here I've got cosine of x. So I need a replacement for this cosine of 2x, a double angle replacement. But if you remember back to the cosine of 2x, there's actually 3 different replacements for the double angle for cosine, and I have to pick the right one to use for this problem. So if you recall that cosine of 2x could either be cosine squared x minus sine squared x, cosine of 2x could be 2 cosine squared x minus 1, or cosine of 2x could be 1 minus 2 sine squared x. All 3 of those forms are a correct replacement for cosine of 2x. I need to pick the one that's going to give me a good result in continuing on solving. So I look at this and I see that the other trig function, or the trig function in here in another term that doesn't have the 2x, it just has x as the cosine function. And I want this all in cosine function if I'm going to be able to solve it or have a common factor that comes in. So with cosine 2x, I want to use this one in this particular example because it's the same trig function, and then it'll be quadratic in cosine x. So we're going to take out the cosine 2x and put in 2 cosine squared x minus 1 is equal to 2 cosine x minus 1 from the original question. All right, now it's quadratic in cosine x, so I want everything on one side set equal to 0. So that's 2 cosine squared x, and then minus 1 minus 2 cosine x plus 1 is equal to 0. And then my negative 1 and my plus 1 combine and remove, and so I'll have 2 cosine squared x minus 2 cosine x is equal to 0. Now, when I factor out 2 cosine x, I get 2 cosine x, and I'll divide into the 2 cosine squared x, that'll give me cosine x. And then 2 cosine x divided into negative 2 cosine x is a minus 1. It's equal to 0. Set each factor equal to 0. I'll get 2 cosine x is equal to 0, or cosine x minus 1 is equal to 0. Divide both sides by 2. Well, 0 divided by 2 is still 0. So that's cosine x is equal to 0, or add 1, cosine x is equal to 1. So again, we want to think what angle in the span from 0 to right up until 2 pi has a cosine ratio of 0. Well, cosine of the angles that give me out 0 are at the angles of pi over 2 and at 3 pi over 2. So x is pi over 2 at 3 pi over 2, and the angle who gives me a cosine ratio of 1 is the angle 0. So for part C, our answers are pi over 2, 3 pi over 2, and 0. Now I wrote all of these angles in the order in which I found them. Sometimes people like you to put them in increasing order from smallest to largest, or especially if you're on online homework system, it might tell you like which order you need to put the list of the angles in. But that, just want to keep track of that to make sure that you report them the way that they've requested, so you don't get it wrong just because you reported it wrong, that you actually get credit for the good work that you've done.